Hi guys, welcome back to AP Stats. This is Mr. Robeson. Today we are looking at regression lines, particularly least squared regression lines, and then we'll talk about how to interpret the slope of a regression line. All right, so what is a regression line? It's a line that predicts how a response variable y changes as an explanatory variable x changes. It's the line that fits the graph, basically. So it's the line that tells us what's going on with the points in the graph. All right, so usually we're just going to write it as an equational line. Before, when you did this, you wrote things as like y equals mx plus b, probably when you were in algebra, maybe algebra 2, where m was the slope and b was the y-intercept. Well, we do things a little different here in stat. I know, it's confusing. All right, so we start off with the constant first, and then we start building up x terms. So we'd have a constant, then we have an x, then we have like an x squared, an x cubed, x to the fourth, and so on. That's just how we do it in statistics. So that means b is the slope. So b is the slope, and a, the number in front, is the y-intercept. It's what you get when x equals 0. And we don't write y anymore either. We write y with something on top of it, all right? And that is called y hat. Y hat. Yes, literally, y is wearing a hat. It means the predicted y. So we are not actually saying what y exactly equals. Like if you look at this line here, it only has like a couple of points on it. All the other points are not on the line. It's predicting what y equals. It's not exactly what y equals. All right, so if we're going to use x and y, we always define what they are. Most of the time, we will actually skip over that. We won't even use x and y, and I'll show you how here in just a second. All right, so if we look at this line here, first of all, we can tell that it's a negative relationship, a negative correlation. All right, and it does look like linear works best, so it's a negative linear correlation. I'd say it's fairly strong. Oh, strong negative linear correlation. Oh, we just did Duff's, and there's nothing unusual. All right, so now let's see, our x is going to be age, and our y is going to be average emails per day. So what we would do is we would say that the average emails is equal to some constant. It looks like it's crossing up here right at 35, so it'd be 35 plus b. I don't know what b is. I mean, we could try and calculate b. Doesn't look like it's exact. I'm just going to use b for now. B times age, where b here is our slope. All right, so we don't even have to use variables. We just use the words, and we throw the words in. All right, it's kind of a sneaky little thing we do, but it works. All right, and the meaning of slope here would be, let's see, it'd be emails per age, and age would be in years. So that would be our units there for slope. All right, let's take a look at the other one over here, see if we can do the same sort of thing. So we've got beach visitors. Let's see, we're looking at average daily temperature in degrees Fahrenheit. That's our x. And the number of visitors to, I suppose, the beach here is our y. It does look like there's some sort of linear relationship here. It looks like it's increasing. That's probably not the line of best fit, but that is a regression line of some sort. It looks pretty good, so I'd say this is a strong, it's going up, positive. It looks like it's a line, linear relationship. All right, between average daily temperature and visitors. So our equation would look something like this. We'd have visitors hat. Instead of saying y, we just put visitors with the big hat on it. Equals our y-intercept. I don't know what it is. We'll just leave it as a for now. Plus b, our slope, times our temperature. All right, just like that. All right, so we will actually learn how to find the slope here today, and we'll learn how to find the a here in a minute. And our slope would be in visitors per degree Fahrenheit. So for each degree Fahrenheit, we have an increase. We'd have an increase in visitors. All right, and we'll get into that more in a couple of slides here. All right, so the specific line that we're going to find is called a least squares regression line, or least squared or least square regression line. All right, it's a unique line. So there's only one for each set of data. That exactly is the least squared regression line. That makes the sum of the squared vertical distances of the data points from the line as small as possible. All right, this is always what we're going to use, but it takes all the points. So we got like points here, 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 and here. And it imagines where would the line be to make this vertical distance from the line to the point. If we square that, we make squares out of it, square it, and we add up all those boxes, the area of all those boxes, this is the line that's going to make the least amount of area. All right? We don't necessarily have to know that. It's not super important. All right? But there is a way to find the slope. So there's a formula for slope. It will equal, so that is the slope, B, equals R. Remember, R was our correlation coefficient. It had that long formula to derive 1 over n minus 1 times the sum of the z-scores for the x's times the z-scores for the y's, whatever. Don't have to know it. Times the standard deviation of y divided by the standard deviation of x. I haven't really seen this formula show up much on the AP exam, but it is fair game and it is on the formula sheet. So that's the slope. And then it goes through a point, and the point it goes through is, see how we have x bar and y bar? That's the mean x and the mean y. So it calculates the mean x and the mean y, not x, and it goes through that point, and it calculates the slope based on the standard deviations of the y's, the standard deviations of x's, and the r, and finds the mean x and the mean y, and it makes the equation of a line through that. Luckily, we don't have to do this all on our own. Our calculator is going to do this for us. But once we've got that line, we can use it to what's called extrapolate information. Extrapolate means to predict. So we can predict where points would be on the line here. All right? Notice, even if we predicted these actual points, we wouldn't be exactly right. We'd be off on every single one of these. So it's not an exact, it's just to predict. All right? And be careful, because we can only predict within our domain. So like here, the numbers go from like 3 to 8. So we wouldn't want to use this line to predict what happens when x is 500. Right? It's just too far away. Right? So we want to be close to our actual values when we do our predictions. All right, so how do we interpret the slope? All right, so that is something they love to ask on the AP exam, is they'll ask you for a sentence interpreting your slope. We can use the same sentence. All right, so it's just, we have a model sentence and we just fill into it. So suppose the slope of a least squares regression line relating the grades in AP statistics compared to the number of missing homework assignments is negative 3.5 points per missing homework assignment. First thing we want to do is we want to write the slope as a fraction with 1 on the bottom and with units. So our slope is negative 3.5. Well, we can just say it's negative 3.5 over 1. Real easy. Just put 1 on the bottom. And this is, so the top was your statistics grade. And on the bottom was missing homework assignments. All right, so it looks like our statistics grade goes down 3.5 points for every 1 missing homework assignment. That's basically what that means, but there's some other important words. So we need to have on average, because this line does not exactly match up with our points, as you saw in the last slide. So we have to have that on average, and we have to say that we are predicting because it has to do with y hat. It's not y, it's y hat, so we're predicting. So what we would write for this one is we would say, on average, for each increase, always increase here, by 1 missing homework assignment, so whatever's on the bottom, x is on the bottom, by 1 missing homework, we predict, got to have that we predict, that's one of the things they're looking for, or the on average, that's I put them both in. And let's see, now, we're going down. So down means decrease. So we don't need and, we can just say a decrease. Oops, I was putting words together. Decrease in whatever y stands for, our statistics grade. By, and then we say what was the slope on the top, 3.5. We don't use the negative sign because we took care of it with the decrease. All right, we already took care of it there. By 3.5 points. All right, so on average, for each increase by one missing homework assignment, we predict a decrease in statistics grade by 3.5 points. That's what the slope means. All right, you may have other sentences that you learned in Algebra 2 or whatever, maybe pre-calc, Algebra 1, who knows. This sentence will get you full credit on the AP exam. And that's what we're looking for here. So we got to have this on average, that's new. We got to have this we predict, that's new. All right, 1 unit increase in the bottom, then we have either an increase or a decrease by whatever the unit is on the top. All right, so ordinarily in class, this is where we would break out a giant bowl of starbursts and we would play the crane game. You would take your hand, you would measure your hand across from your pinky tip to thumb tip. Looks like this is 20.5 centimeters. And we would record that length. And then I would have you take your hand and stick it into this giant bowl of starbursts and see how many starbursts you can get without turning your hand under it, just going straight down, grabbing, and pulling straight back up. All right, so this is data from a couple years ago, the students in the class. So I've already put this in my calculator. If you want to pause the video, put it in your calculator so you can do this along with us. It is kind of a long data set, so you might just want to follow along. So it's in my calculator. I put this hand width in L1. So this went in L1, starburst grabbed went in L2. So I've already got it there. All right, so how do we find the line now? So once we put the data into lists, that's step 1, we go to stat, our stat menu, go over to calculate, and then we are choosing number 8, lin reg A plus BX, because we want B to be our slope. All right, so let's see. Where's our calculator? There's our calculator. So let's turn it on. Let's see. Looks like I was doing some other stat. So stats, edit, just want to make sure it's there. Look, there it is, L1 and L2. I got other stuff in L3 and L4, it doesn't matter, but it's in L1 and L2. So now we want to go to stat, calc, and we are going to number 8. Now I know there's another lin reg right here, that's AX plus B. We want A plus BX. All right, so we're going to press enter there. We're going to tell, say, our X was L1, our Y is L2. We don't need to worry about the rest of that stuff. And we're going to press calculate. And voila, it gave us everything. Now remember, if we're missing the R and the R squared here, we can go to mode and we can turn the stat stuff on. So it might be turned off when we want it turned on. So now we've got it for our statistics, or our starburst line. Let's see if I can move the calculator out of the way here and we can write this down. And then we can just kind of put the calculator off to the side. We've got, let's see, our Y is starburst. So starburst equals A plus B times X. So let's see, our A is 1.07. 1.07 plus 2 decimal places is usually fine, by the way. 1.19. 1.19 times your hand width. And this is in centimeters. So I'm putting the units there, everything, just hand width in centimeters. There it is. So there's our equation. Notice I didn't write it with X and Y like we used to. I just went ahead and put the words there. And I have to have the hat here. The hat is important. That means predicted starburst. So now use the line to predict the number of starbursts someone with a span of 24.5 centimeters could grab. All right, well, the predicted starbursts, there's my hat, equals 1.07 plus 1.19 times 24.5. Whatever that works out to. Done. What is the y-intercept of our least squared regression line? Well, if we plug in 0, we get 1.07. All right, and let's say what that actually means. So for a hand width of 0 centimeters, we predict 1.07 starbursts grabbed. Now that, to me, that doesn't make sense. It's not possible to have a hand width of 0 centimeters, and if you had, that means you have no hand. And if you have no hand, how are you going to grab a starburst? doesn't make sense to me. So this is going to be outside of our domain. So it's probably not going to be important for using prediction. So outside of domain. So we probably don't want to use that to predict when our hand size is 0. All right, can we use the line to predict the number of starbursts with someone with a span of 50? Well, if we go back to our data, the highest X value, so we had a 28, we had some 28s, so our highest hand width was 28. So then do we want to, do we want to use that data to predict someone with a 50 centimeters? Like, so we went from 20 centimeters to 28 centimeters, and we want to use it to predict at 50. So this is definitely not in our domain. I mean, we could still plug it in, but we would be very careful about it. I mean, if we had the option to say no, we'd probably want to say, no, that's probably not a good idea. All right, and the reason why is maybe 50 centimeters is too big to grab out of that bowl. So like the numbers wouldn't be legitimate. Like they would need a bigger bowl than what we had. All right, interpret the slope of this line. All right, so interpreting the slope, we just went over that. So we say our slope is 1.19. So we'd say 1.19 over 1. And the top units are, the y units are starbursts. The bottom units are centimeters in hand width. So then our sentence is, on average, for each increase in hand width of 1 centimeter, we predict, let's see, it's positive, so it's going to be an increase in, let's see, our units here is starbursts. And we could probably say starburst grabbed because that's what we're doing. By 1.19. Boom, done. All right, and last one here, interpret our correlation coefficient. So what is our R value? Well, it disappeared. Let's see if I can bring it back. Let's press enter again. There it is. So our R value is 0.767. So 0.77, that's actually pretty high. All right, if we look at the data though, we have to look at the data to see is it linear or not first. So we do want to check out the stat plot, and I think we'll check that out next, or we can check that out now. We did go over how to do that last class, so let's check that out now to make sure it's linear before we interpret our R. So second, stat plot. We've got that turned on already. It's set for dot plot. Our lists are in the right spot. Let's check out the graph. Usually it's zoom 9. There it is. All right, so that looks fairly linear to me. They're lining up pretty good, except for this guy. Looks like we might have an outlier there. All right, so this would be so it's over 0.7, so I'd say it's a strong. It's a positive number, so I'm going to say it's positive. And I'm going to say it's linear, and that this is from looking at the graph. So the linear part comes from the graph. The other two parts just come from the number itself. All right, so one more example here, and that's it for this one. So a bank manager does a least squared regression analysis on some data. She finds that the number of years people have been working at the bank increases, the number of customer complaints per month about them decreases. The data she gets from her analysis is A is 15, B is negative 0.42, so this is our slope. This is our y-intercept. And this is our R is our correlation coefficient. All right, we'll talk about R squared later. Right, so you may have seen that last one. Write out the least squared regression line in context. So we've got the predicted, and let's see, the number of customer complaints. So the predicted complaints, that's what was decreasing, equals our y-intercept, 15.53, plus negative, so we could say minus 0.42 times, and she finds that the number of years people have been working. So our x is years working. It is years, right? Yes, years. Interpret the r value, the correlation coefficient. So our r is negative 0.86. So it's negative. And it's a high number, so we want to say it's strong. However, we do not want to say it's linear because we need a graph in order to say linear or not. So we don't want to say anything about that. What is a reasonable domain for this equation? All right, well, how many years could we be working at this place? Well, clearly we could plug in 0 and 15 complaints. That seems reasonable. All right, so we could start at 0. So from 0 years to, well, would it make sense for this to be a negative number? Probably not. You can't have negative complaints per year or per month about somebody. All right, so we could just solve this. So we could subtract over the 15.53, divide by the 0.42, and that would get us the number of years. So let's do that real quick on our calculator. So we got 15.53 divided by 0.42. I realized I left off all my negatives here. That's okay. They're just going to cancel out. 36.9, so roughly 37. So this was negative here. The two negatives do cancel out. So about 37 years. All right, because after that, it's going below the x-axis. It's just not going to make sense. Extrapolate the number of complaints in a month for a worker with 10 years experience. All right, well, that's our x value. That's years, so that's going in here. So we get that the predicted complaints, predicted, so we got to have our hat, is equal to 15.53 minus 0.42 times 10. So this is going to be 15.53 minus 4.2, which gives us, what is that, 11.33 complaints. And there we go. And this is within our domain, so this makes sense. If we were predicting for 80 years, that would not make sense. All right, so that's how we get least squared regression lines and how we use least squared regression lines and how we get slope from least squared regression lines and interpret it. Next time, we'll look at something called residuals. So I'll see you again soon.